this video, we're going to be considering dams and hydroelectric power plants. So there was a big scheme in the 1950s and 60s in Australia called the Snowy Mountain Scheme, where the government undertook the damming of a lot of rivers in New South Wales and Victoria in order to irrigate a lot of land and to generate electricity. As part of this scheme, they built 16 dams, 7 power stations, a pumping station, and 225 kilometres of tunnels, pipes, and aqueducts. So in doing this scheme, they built dams which flooded a lot of land, and there was a few towns, including Adaminaby, that needed to be moved, as the old site of Adaminaby is now under Lake Eucumbene, which was formed by the damming of the river.
So this photo shows Lake Eucumbene a few years ago. Lake Eucumbene is a completely man-made lake. A few years ago there was a big drought and the level of the lake dropped a lot, and you can actually see that all the trees which were flooded when Lake Eucumbene was formed have now started to appear again. So this is actually revealing the old town site of Adaminaby before it was moved to its new location.
So let's consider now how hydropower plants work. Hydropower plants work by basically converting the gravitational potential energy of the water in the river into electrical energy. So to understand how this happens, we first need to understand the law of conservation of energy. So we've met the law of conservation of energy briefly before, and we'll be looking at it again later. The law of conservation of energy is a very, very important law in physics. So what the law of energy conservation says is that energy in a system is always conserved unless you add energy to the system. So there's two ways of adding energy to the system. One is to do work on a system, and one is to add heat to the system. So in the kettle, we were adding heat to the system. What we're going to be looking at now is doing work on the system to increase its energy. So there's two main ways that energy can be stored within a system. One is as potential energy, and the second is as kinetic energy. So potential energy is a kind of stored energy. One way to store the energy is in the gravitational potential energy, and kinetic energy is the energy of movement. So when something's moving, it's got a lot of kinetic energy. So let's look at gravitational potential energy now. So gravitational potential energy near the surface of the Earth is given by the formula U, which is the symbol for gravitational potential energy, is equal to m times g times y, where y is the height of the object. So let's consider how this equation comes about so that we can work out the limitations on this equation. So we've said that to change the energy of a system, we need to do work on the system. So consider this jug of water on the floor. If I lift it up, how much work am I going to do on it? Well, work is equal to the force that's applied times the distance that the object is moved. So first of all, have a think, what force do I need to overcome to lift that jug up? Hopefully you realise that it's the weight force caused by the gravitational force which I need to overcome to lift the jug up. So let's call this initial height y1. Now what I'm going to do, lift the jug up. I'm doing work on the jug to overcome the gravitational force, and it's now at a height y2. So the change in the height between the floor and here is given by y2 minus y1. And so we could call that h. h is equal to y2 minus y1. And the gravitational force is given by mg. And so the amount of work I've done to lift it is given by mgh, or mg times the change in y. And so because I've done that amount of work on it, I've given it that amount of energy, and that is what has caused the change in its gravitational potential energy. So it now has that energy stored in here just by being at this height. If I let go, it can now fall back to the earth and gain gravitational kinetic energy as it does so. So let's do that now. Here's the water going back down. So as the water falls back down, it's gaining kinetic energy. Now it's possible to put a paddle wheel or a turbine in its path, and the falling water can then do work on that turbine. So we're effectively converting the gravitational potential energy into work done on the turbine, which in turn gets changed into electricity. So let's do an example now of using the mgh formula.
Before we do an example, let's just consider one thing. What would happen if I had the jug of water and I moved it horizontally, but I didn't change its height? Its height remained the same. What would happen to the amount of work done on the jug in this case? Well, in this case, work is equal to the force times the distance. But in order to apply this equation, the force and the distance or displacement actually need to be in the same direction. So in this case, the force that I am overcoming is the weight force. And that is actually perpendicular to the direction that I was moving the object. So in the case where we move an object horizontally and the only force being applied is the gravitational force, you do not do any work. So the work is actually equal to 0 because these are perpendicular to each other. Okay, so the question is, 480,000 megalitres of water is stored in Lake Eucumbene. The dam wall is 116 metres high. If all this water was to be released from the dam, how much gravitational potential energy would be lost? You may assume that the average height of the water is half the height of the dam. So we have a dam wall like this. It's 116 metres high. We have it filled with water. So the top part of the water is at 116 metres, down here we're at 0 metres. And so the average height is half this height here, which is what this is telling us. And so to calculate the change in gravitational potential energy, we've got that U is equal to mgh. And now, so we need to work out what mass of water falls from what height. So we've got 480,000 megalitres. So that's 480,000 times 10 to the 6 litres. And because it's water, 1 litre is 1 kilogram. So that has converted it into kilograms. And then we times it by 9.8. And then we need to times it by the height it falls. Well, the top part falls from 116 metres, but the bottom part falls 0 metres. So the average height is 116 on 2. And this is equal to 58 metres. So we can type all this into the calculator. When we do that, we get 2.73 times 10 to the 14 joules. So an awful lot of energy would be released if all this water was allowed out through the dam.